Okay, I want to talk about simple radical form for a minute. So when we have the square root of 25, it really means what times itself equals 25, right? So this 25 is a perfect square because 5 times 5 equals 25. So 5, right? And you could also make an argument negative 5 times itself would equal 25. So this has a positive and a negative root actually, but we're just going to list the principal root here. That's usually the way it's done when we're just simplifying an expression like this. Okay, but let's say we have the square root of 50. Now this is not a perfect square, so you could just, it's going to be a little more than 7, right? 7 times 7 is 49. You could put it into a calculator, and it's roughly 7.1, something like that, okay? So nothing wrong with that, but that's a decimal approximation, and it's just approximately equal to that, okay? So I want to talk about simple radical form. We're going to do something else. This is not in simple radical form. So there's different ways that you can, so yeah, this is going to be simple radical form here. There's different ways that you can approach this, and this is the way that I teach it, and other teachers do it differently. So if you got a different method that's working, that's fine. So what I like to do is think of a multiplication problem whose answer is 50, and I want to use integers, so I don't want to use any decimals or fractions, and I don't want to use 1. 1 times 50 is no good, but anything else will work. So I got some different options here. I could do 2 times 25 or 5 times 10. It doesn't matter. You can pick any one of them. So let's say I chose 5 times 10, okay? And so now I've broken 50 up into 5 times 10. And now I'm looking at this. 5 is a prime number. I can't break that down any further, but I could do something with 10, because 10 would be 5 times 2. So I could break this down even further, like so, right? 5 times 10 would be 50. 5 times 5 times 2, okay? And now what I'm doing is looking for twins, and I found some twins, okay? So if you think of the radical as a jail, there's only one way you can make a break from the jail. You need a twin, okay? Because one of your twins is going to distract the guards and sadly get shot and dies. But the other one will get out, okay? So when I've got a pair of twins, they're going to make a break for it. One will get out, one sadly will not, and just disappear. And then if you don't have a twin, you're just stuck in the jail forever, and boom, there is simple radical form. So 5 root 2 is simple radical form of the square root of 50, okay? So why don't you guys try this next problem. You can pause the video if you like, so try to break it up and then take out twins. By the way, they can be grown-up twins. You don't have to really break things down into prime numbers. If you find some twins along the way, then you can take them out as you go, okay? So first thing I'm thinking, 200, that's 2 times 100. And then 100 is 10 times 10. So I've got it down to this. Now what I was talking about with the grown-up twins, yeah, I could break down the 10s further, and there's nothing wrong with that. But as soon as I find twins, I just say, oh, these can make a break, right? Got a jailbreak on our hands there. So one of those 10s is going to get out, one won't, and then the 2 is trapped in there forever. Oops, I'm off screen. And then I can't do anything else with the 2. Sometimes you'll end up with some multiplication to do on the outside if you got different parties that are breaking out, or if you have different things that are left on the inside, you might need to multiply them together, but here there's nothing else to do. 10 root 2 is simple radical form of the square root of 200. Okay, now let's extend this. We can also do this when we have variables. I'm going to use the same technique. So I'm just going to start breaking up the 8. And I'm going to do this all in one step. It would be 2 times 4 would be 8. Right? But 4 would be 2 times 2. So if I broke down the 8 all the way, there we go. Okay? And then for the x's, x to the third means x times x times x. Y to the fourth. Okay? Now you don't necessarily have to write those all out, especially if I had x to the 17th. I probably wouldn't write out 17 x's all multiplied together. But you want to be thinking how many pairs of twins do you have, right? So when I'm looking at the 2's, well, I've got triplets here, so that's kind of interesting. What happens there? Well, it's only 4 twins, okay? So one of the triplets is just going to get left out. So this one is just going to stay in there, okay? But one of these will make a break. And then for the x's, I've also got triplets. So these two will do a break. This one will just stay in there. And for the y's, I've got two different pairs of twins, right? So, and there's one of each of these pairs of twins that got out from each pair, right? So I got a 2 that got out right there. I've got an x that got out. I've got a y that got out. And I've got another y that got out. And then what I have left in the jail is a 2 and an x, okay? So all the pieces that get out should be multiplied together, like so, right? So then I will simplify the part on the outside. So this would be 2x y to the second, right? There's 2y, so y to the second. And then this would be 2x. And there is simple radical form, okay? All right, I've got another problem up there at the top. Sometimes you might need to multiply things together that are in simple radical form, okay? And the way you can do this, just multiply these two pieces together and these two pieces together. In other words, I can rearrange the parts here because everything's multiplied together, right? So I could write this as 3 times 2 times the square root of 2 times the square root of 6. Commutative property of multiplication allows me to do that, okay? And then, hey, I can just multiply those together, okay? And when you're multiplying radicals together, you can put them under the same roof. So this would be 2 times 6 under the radical, okay? And then I'm looking at this and thinking, oh, well, 2 times 6 is 12, but I'm just going to break it apart looking for twins anyways, right? Because I want to make sure all of the twins make a break here. So I'm just going to keep working on this. So the 6 I can break up into 2 times 3. By the way, if I said 3 times 2, the twins don't have to be next to each other. You just have to have the same numbers underneath the radical. Okay, so those will make a break. So we already had the 6 on the outside. Whoops, sorry. We already had the 6 on the outside. Now a 2 is going to make it out. Another one won't. And then the 3 stuck in there. Okay. And I simplify that, 12 root 3 is my final answer. Okay. Separate that here. Okay, so you could pause it and try this one out if you like. I'm going to get straight to it. So I usually won't rewrite this in the different order. I'll just think, okay, I'm going to multiply it together, the parts on the outside. And then I will multiply the parts on the inside. So I'm thinking, oh, I'm going to have 5 times 5. And yeah, that's 25, but I'm just going to break it apart anyways, right? And then I've got 1x over here. And I got 3 more x's from the 5x to the third. So there's all the parts underneath the radical, right? I got 2 5s and 4 x's. Okay, and then I'll start looking for twins. There we go. So a 5 will get out, an x will get out, another x will get out, and hey, there's nothing left in the jail, so we don't need it anymore, okay? And then I just multiply this all together. This is going to be 30x squared. Okay? So, simple radical form, you need to take out the twins, okay? Another thing you need to do is make sure there are no radicals in the denominator. It's just the rules. I'm not sure why, but simple radical form, no radicals in the denominator. There's no twins to take out here, though. So what am I going to do? Well, since I don't have a twin down here in the denominator, I am going to clone one. Okay, so I take my root 3, and I'll just multiply it by root 3. Now, I can do that as long as I do the same thing to the numerator, because now I'm really just multiplying this fraction by 1, right? Root 3 over root 3 equals 1. So I'm not changing its value, I'm just changing its form. Okay? And then I'm going to multiply straight across. So 2 times root 3 on the top would be just 2 root 3. Okay? On the bottom, I can put these under the same roof. And then, hey, got a pair of twins, or it's just the square root of 9, right? Which would be 3. That's another way to think of that. Okay? Some people will look at this and say, wait, can I reduce the 3's? Well, you can't do that because one is under a radical and one isn't. If they're both under the radical, then I could do that. Or, for example, I could also, if I had 4/6 in that spot, I could reduce it to 2/3 because those are not underneath the radicals. But this one is good to go. Okay? So you can go ahead and pause it and try the next one if you like. So I'm thinking, okay, can't have that radical down here. Let's clone a root 7 so that I have myself some twins, and I can make a break. And then I'm checking it to see it's reduced. This is reduced. I can't do anything with those 7s because one's in jail and one isn't. And 3/7 is already reduced. Okay. All right. Next up, another one, kind of similar. So I'm thinking, all right, I could break that up into 2 times 3, but there's still no twins. So I'm just going to do this. That'll give me 2 root 6. And, you know, this is going to come out to just 6 down there. So you might probably notice that pattern already. So I've got 2 root 6 over 6, okay? And I'm looking at this, can't reduce the 6's, but hey, I can reduce this, right? 2/6 is going to reduce to 1/3. So I'm going to write it like this. You could write 1 root 6 over, but you don't need the 1 out there. I can already see there's one of them, right? So that's just kind of redundant. Okay. All right, so simple radical form. What do you need to do? There's 3 things. Reduce all fractions. Remove all twins. And then there's that rule, no radicals in the denominator. It's okay to have one in the numerator, but not in the denominator just because. Wasn't my idea. But that's the rules. Okay, now this is super important in this chapter. This might be something that you remember from algebra, but my experience is that a lot of people have forgotten about simple radical form. And a lot of times in this chapter, you're going to want to answer in simple radical form. Okay, so let's actually get to 9.1 then. Let's get to the Pythagorean Theorem. Okay, and I've got a little illustration. Maybe you remember the Pythagorean Theorem. You've probably seen it before. But here's a little illustration. So let's just say that this triangle is a 3, 4, 5 right triangle. Okay, well, we've got 3 units there, 4 units there, 5 units there. I just wrote it on the inside. Okay. Now, if we think about how many squares there are on this bigger square on the left, well, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 of them if you count them up. Okay, and it kind of makes sense because it's this 3 by 3 square. 3 squared, right? That's why they call it 3 squared. All right, and if you were to count these in this box, there's 16 of them because it's a 4 by 4. I'm definitely not going to count these, but there's 25 because it's 5 by 5. Okay. Now, who cares? Well, if you look at this relationship, if you take 9 plus 16, it equals 25, okay? Which really means that 3 squared, because that is 9, right, plus 4 squared equals 5 squared, okay? And that brings us to the Pythagorean Theorem. Okay, this is a right triangle, and this relationship works for this right triangle, but it works for any right triangle. Okay, and here is the Pythagorean theorem itself. Okay, so A and B are going to be the legs of a right triangle, and C will be the hypotenuse. So I assume you remember what the hypotenuse is, but it's super important that you can identify the hypotenuse. It's the longest of the 3 sides, but sometimes it's hard to tell what's the longest. It's always across from the right angle, right? Okay, so let's try that out. Okay, and whenever possible, I'm going to answer in simple radical form. Okay, so let's see what happens here. So I'm thinking Pythagorean theorem, a squared plus b squared equals c squared. And it's really important that I know which piece is the c. So here, across from the right angle, this is the hypotenuse. Okay, so I'm going to put that in the c position. Okay, 8 and 6, which is a, which is b? It doesn't matter. I'm just going to say, put it like that, but it doesn't matter because 8 squared plus 6 squared is going to be the same as 6 squared plus 8 squared. So these, the a and the b, are interchangeable, but you need to have the x over there for this particular problem because that's the hypotenuse. Okay? And then I'm going to work on simplifying this. So 8 squared is 64. 6 squared is 36. Okay, and when I add these bits together, I get 100. Okay, and now to undo a square root, I don't really want to know what x squared is. I want to know what x is, right? So I'm going to take the square root of both sides of the equation. Okay, and technically, like if I just had a math problem like this, so when I take the square root of x squared, here, maybe I should write it like that for the first one. So technically, I could say that this root 100 could be positive or negative 10, because 10 times 10 is 100, negative 10 times negative 10 is 100. And if it's just an algebra problem, that will work. But I can't have a negative side to a triangle. That can't be negative 10 units, right? So I'm just going to use the principal root here. So x will equal positive 10. Okay, so for right triangles, the sides are always going to be positive. Okay, and this is in simple radical form, and right, there's no radical involved. Okay, on this next one, the c is going to be this, right? That's the part that's across from the right angle. So that's my hypotenuse. Okay, so I'll say x squared plus 12 squared equals 13 squared, or you could have said 12 squared plus x squared. That would be fine too. Okay, so I'll start simplifying these bits. Okay, and my strategy is to get the x squared by itself, and once I do that, I'll take the square root of both sides. Hey, this is nice. I got a perfect square there. So x is going to equal the square root of 25, and it's got to be a positive number, so this is going to come out to 5. Okay. All right. So in both of these problems, I had a 6, 8, 10 triangle here. By the way, that's just a 3, 4, 5 triangle doubled, right? And over here I had a 5, 12, 13 triangle. So these are both examples of Pythagorean triples, and that just means we've got 3 integers that work with the Pythagorean theorem. So that means it's 3 integers that could be the sides of a right triangle. Okay. So you'll see there aren't that many Pythagorean triples that use relatively small numbers, so you'll kind of see the same ones over and over again. Okay, so we talked about a 3, 4, 5 a little bit, and I could multiply that by 2 and all of those numbers and get a 6, 8, 10, or I could multiply them by 3 and get a 9, 12, 15. That would be another Pythagorean triple. Okay. So you could double or triple, quadruple that, and you'd still end up with a Pythagorean triple. Okay, and this list goes on and on. We could do this all day. It's an infinitely long list, but there are some very common ones that you'll see. I really just want you to know what a Pythagorean triple is for now. Okay. All right, so let's try one that is not a Pythagorean triple. So same kind of problem here. We're still solving for x. I've got a right triangle, so I know I can use the Pythagorean theorem. This is the hypotenuse. So I'll say x squared plus 8 squared equals 12 squared. And I'll simplify those exponents. Now I'm going to subtract 64. Okay, and then I'll take the square root of both sides. Okay, so hey, that's not a perfect square. You can put it into a calculator and get a decimal, but let's not do that. Let's put this in simple radical form. So I'm thinking of a multiplication problem with 80 as the answer. I just chose 8 times 10, but he could have done 2 times 40 or whatever. Okay, so let's break up the 8 further. 8 is 2 times 2 times 2. And then 10 is 2 times 5. And then I'm looking for twins. Okay, so there's going to be a 2 that gets out from this group, a 2 that gets out from that group. 5 will not get out. And then simplified, this is going to be 4 root 5. Okay. All right. So here's a throwback problem. Could a triangle have sides of 1 meter, 5 meters, and 10 meters? Well, if you remember back a couple chapters ago, if you take the largest side, so let's say that this is 10 meters, and let's pretend this is a river, okay? And we want to cross it, we want to build a bridge, and we're going to use the 2 smaller parts to try to build the bridge. So let's see, I'll put the 1 over there, something like that, and I'm just sketching this, obviously not measuring this, but those bridge pieces aren't big enough, right? So that the sum of the 2 smaller pieces has to be greater than the bigger piece so that you have enough bridge to cover the river. Okay, so this is going to be a no. So just a reminder about that because that's going to come up again. Okay. All right, so the Pythagorean theorem has a converse, and that says that in any triangle, if this relationship is true, where the sum of the squares of the 2 legs is equal to the hypotenuse squared, then it's a right triangle. Okay, so we can just flip that statement around, right? If it's a right triangle, then a squared plus b squared equals c squared, and the reverse is true. Okay, so we can look at any triangle then and determine whether it's a right triangle or not. Now, how do I know what the potential, I don't know if it's a hypotenuse yet, but how do I know which might be the hypotenuse? Well, it's got to be, if there is a hypotenuse, it would have to be the largest of the 3, okay? So I'm just going to test this out. So either this is going to be true or it's not. If it's true, it's a right triangle. If it's not true, it's not a right triangle. So let's see. Okay, 7 squared is 49, 24 squared is 576, and 25 squared is 625. Okay, and when I add those together, sure enough, both sides balance out, and so this did work with the Pythagorean theorem. Therefore, this is a right triangle. Okay, so hey, that's another Pythagorean triple then, another very common one you'll see, 7, 24, 25. Okay. All right, so right triangles, we've got this relationship. We already talked about this. Well, what happens when we have an acute triangle or an obtuse triangle? Okay, so let's say I'm going to take this 6, 8, 10 triangle over here, and I'm going to alter it. So I want to make an acute triangle. So those 2 sides that I just highlighted, I'm going to think of that as a hinge where the right angle is, and I'm going to close it a little bit. Right now it's 90 degrees, but let's just close that hinge a little bit so that I have an acute triangle. Okay, so I'm still going to say that this is 8 and this is 6. So that was my hinge there that I closed a little bit. Okay, and then let's say now that I closed this, this can't be 10 anymore. It's got to be less than 10. Let's just make it 9 for a nice round number. Okay, so this would have to be an acute triangle then. And let's see what the relationship is when I take this when I try to do a squared plus b squared and compare it to c squared. So a would be either 6 or 8 here. Okay, and I'm not going to say equals yet because I don't know if these equal each other or not. Let's see what happens. So I've got 36 and 64, 81. And when I combine 36 and 64, I get 100. So those are not equal, right? The 100 is greater than the 81. So now I can go back up here, and this relationship is going to hold true for any acute triangle, okay? So now I can say, so, to get the acute triangle, the way I think of it is you kind of shrink the hypotenuse a little bit. That closes the hinge. And so this relationship is true for all acute triangles. So you can do a little test. We could already do a test to see if it's a right triangle. Now we can see if it's acute. And we can also test if it's going to be obtuse. Okay, so this time I'm going to open that hinge, so this can still be 8 and 6. And since I open this hinge, this can't be 10 anymore. Let's have it be more than 10. I'll call it 11, just to give us nice round numbers. And when we test a squared plus b squared and compare it to c squared, you can probably guess what's going to happen. It's going to come out to 100 again. This is 121. And so the c has grown compared to the original c, so that means the c squared will also have grown, right? Okay, so next example. Could a triangle have these side lengths? So first thing I want to do is see if I have enough bridge to cover the river. So this would be the river because it's the biggest one, right? So I want to check, is 11 plus 14 greater than 15? Definitely, right? This is 25. So my answer for this first part is yes. I didn't leave myself much space there. Okay, so now here comes more of the work is going to be the second part. Classify the triangle. I'm going to say if this is a right triangle or acute or obtuse. So I'm going to try a squared plus b squared and compare it to c squared. It's either going to be equal or they're going to be greater or less than. So let's see. Remember, c would have to be the largest of these. A and b are 14 and 11 in either order. Okay? And so let's see. 14 squared is 196. 11 squared is 121. 15 squared is 225. And then when you combine these, we're going to get 317. And 317 is more than 225. So that tells me a squared plus b squared is greater than c squared. So, I know I've got the chart right there. This is going to be acute. But if I didn't have that in front of me, I'd think, oh, the c has shrunk from a regular triangle. And that means that would close that hinge. So this is going to be acute. Okay. All right. Same kind of question. So you could pause it and try this one out. So first thing I'm thinking, 8 plus 9, is that greater than 13? Yes, it is. So I have enough bridge pieces. And then let's classify. Okay, so this would have to be the hypotenuse if this is a right triangle. That's going to be the C piece. Okay, and then 64 and 81 is going to be 145. So in this case, that situation, so I'm thinking from the original Pythagorean theorem, the c is grown, so the c squared is grown. That would open that hinge. That means I'm going to have an obtuse triangle. Okay. All right. A lot in this section. Let's find the area of this triangle. Some people are going to say, oh, I can find the area of a triangle. It's 1/2 base times height. This looks like a right angle there, so 1/2 of 10 times 10, 1/2 of 100 is 50. So my area is 50, but they're wrong. Okay? Because they're making the assumption that that is a right angle just because it kind of looks like one. But I don't know if that's the case. Okay? So this is not going to be 50 units. So what I am going to do, and this works great with isosceles triangles. If you find the corner where the two congruent sides meet, so right up there, it's the top on this one, let's just draw in the altitude. So there's the altitude, right? That connects to the 12. There's other altitudes, but I want that one, okay? So what I can do is find the length of this altitude, okay? Because we've actually got congruent triangles. We could figure that out with hypotenuse leg, right? We've got the hypotenuse of both those right triangles are congruent, and then we could use reflexive property like so, right? So those triangles are congruent, so that means that this 12 would get cut in half. So this would be 6, and this would be 6 again, okay? All right, so now what I can do, I can use the Pythagorean theorem, right? If I'm going to call this h for the height of the triangle, I can say 6 squared plus h squared is going to equal 10 squared. One nice thing about Pythagorean triples, you might recognize, oh, this is going to be a 6, 8, 10. That's what the h is going to be, and that's great. If you see that, go ahead and use that. If you didn't notice, you could always do the Pythagorean theorem. Then I'm going to take the square root of 64, which is exactly 8. So this is 8, okay? And now when I look at the original problem, you need to know the area formula for a triangle, which looks like that. I can use, remember to use 12 as your base, not 6. If you use 6, then you'll just get the area of one of those half triangles, right? So 12 is my base. That's my base, and h is my height. And then I just simplify this. So, you know, I'm just thinking, what's 1/2 of 12? That's 6. Okay. Some people try to distribute the 1/2, but you're just multiplying these 3 pieces together, right? So if you had 2 times 3 times 4, you just do 2 times 3 first, and then multiply that by 4. And then I've got 48. Okay, now this is area, so I do want to show that the units are squared even when I don't know what the units are. So I'm going to say 48 square units. Not 50, right? Like I promised, it's not 50. Okay. Similar problem here. You can pause it and try this out. So hey, there's where the 2 congruent sides meet. Just going to do an operation, use my scissors, cut that down like that. That 14 will be divided in half, and now I can use the Pythagorean theorem to find the height. So 7 squared plus h squared is going to equal 12 squared. Okay, I'll subtract 49, that's going to give me 95 there, okay? And then, let's see, I'm running out of space, I'll take the square root of both sides, okay? And when I look at 95, sometimes you'll get things like this that are already in, now I know I can divide 95 by 5, right? So 5 times 19 is, 5 times 19 is 95. But I can't break down the 19 any further or the 5, so there's no twins in there. So this is actually already in simple radical form. Okay. Okay, and then I'm using my base and my height in the area formula. Oh, and I wrote 7, I meant 14. Used the wrong base there. Okay, 1/2 of 14 is 7. Okay, that's in simple radical form, and I don't have the units, so I'll just say that many square units. Okay, and that is it. That was kind of a long one, sorry about that, but that's how it worked out.